Hi guys, so today we're going to do activity 20, chapter 21, enols and enolates. So we're going to do the class and condensation first. As we see, we have an ester that's going to be produced into a B-keto ester as a product. We're going to usually do that with an ethoxy group or a methoxy group. So first, number one, we're going to have to draw our lone pairs. We're also on our heteroatoms, and we're also going to have to do our proton transfer, our nucleophilic attack, and our loss of living group. So first of all, let's draw all of our lone pairs around all of our heteroatoms. So we could do that on all the oxygens. Now we're going to see that the ethoxide is going to attack the alpha proton, and then that's going to create a double bond, and the double bond on the oxygen is going to break, and that's going to be describing our proton transfer. As we see in the next one, the oxygen group is going to collapse back to make the double bond. The double bond's going to attack the carbon on the carbonyl atom, and then the oxygen double bond's going to break, and it's going to be our nucleophilic attack. And then again, our oxygen is going to collapse back down, and it's going to push out our ethoxide group, leaving our loss of living group, and leaving us our product, our B-keto ester. And number two, we're going to also show the mechanism of the following transformations. So we're going to do exactly the same thing as we did in number one. So we're going to have to do our proton transfer and nucleophilic attack and our loss of living group. So we know that the methoxide is going to attack the proton. The alpha proton is going to create the double bond, and then the oxygen is going to come back down. And then we're going to do the nucleophilic attack, where we know that the oxygen is going to collapse back down, and then our double bond is going to attack the carbon on the carbonyl atom, and then it's going to create a good leaving group for the methoxide to leave. On the second one, we're doing exactly the same as we did. So we're going to have to show the proton transfer, the nucleophilic attack, and the loss of leaving group. As we see in this page, we're doing the general schema of the Karla condensation. So we know that the alpha proton has to attack the carbon on the carbonyl atom, and then we kick out the OR group. As we see in the example, we create a single bond and we kick out the OR group. It also shows us how to do it, step 1 and step 2 down there. So now let's do number 3. So predict the product of the following Karla condensation. As we have an ester with a methoxide group. So we're going to draw that. We're going to draw the line from the alpha proton to the carbonyl, and we're going to kick out the methoxide group, and we have our product. The same thing we're going to do to the other ester. We're going to connect our alpha proton to our carbon carbonyl. We're going to kick out the OR group, and then we're going to have our product. We're also going to do the same thing for C and D. We're going to connect our alpha protons to our carbon carbonyl, and then we're going to kick out our OR groups. Now we're going to look into LDA. LDA is going to be a base that's going to attack the ester, is going to create it as an enolate, and then we're going to throw in the electrophile. So number 4, we're going to predict the product of the following Karla condensation reaction. So we see that we have our first ester that's going to react with LDA, and it's going to cause it to become an enolate. That enolate is going to react with another ester, and it's going to form our product. That's going to look like this, our product. Now we're going to do the same thing to the other side. So we're going to, our first ester, we're going to react it with LDA. And remember that the alpha position of one of the protons is going to become our enolate. And then we're going to react it with our second ester with with H3O plus. And this is going to be our final product. We're going to do the exact same thing. To see, we're going to react the first ester with LDA. We're going to make it an enolate, and then we're going to attack it with our electrophile. Then we're going to throw in the electrophile, and we're going to get our product. So now we're going to talk about the Deichmann condensation. This is an intermolecular glycine to form a ring. It's the same thing we've been doing where the alpha proton is going to attack the carbon on the carbonyl atom. Just this time we're going to be forming ring. On this one we're going to be forming a 7 new member ring. So we're going to draw it. Sorry for my drawings, they're a little bit ugly. So then on number 7 and 1 we're going to draw our ester ring. Sorry, we're going to draw our ester and our carbonyl as we see here. And then B, we're going to do the exact same thing. The alpha proton is going to attack the carbonyl it's going to attack the carbonyl carbon, and then we're going to form a new ring. This time we're going to form a 5-member ring. We're going to draw our carbonyl, and we're also going to draw our ester. So number 6, synthesize the following target from the condensation reaction. We're going to cut it half at our alpha position. And the first reactant we're going to draw, it's going to be the one that already has the ester because that's the one that's going to become our enolate. And then we're going to react it with LDA and the other part of our ester. That's we're gonna have to add our methoxide group to it, and then our third reagent that we have to add is H3O+. We're going to do the same thing with the other one. We're going to cut it in half. The one that already has the ester is going to be the one we're going to use our reagents toward. And then we're going to do LDA, and then the second one we're going to use the other part of the molecule that we have, and we're going to have to add our ester group, and then we're going to add our H3O+. So now we're going to go to alkylation, and this is where the alpha position of ketones can be alkylated with primary alkyl halides. So at lower temperatures, we see that it's going to be substituted at the less substituted side, and at room temperature higher is going to be at the more substituted side. And then a new alkyl group is going to form. So then on number 7, let's predict the products. As we see here, we're going to form it at the more substituted side, our alkyl group, which is going to be our phenol with our CH2, as we see here. On number C, we see that a lower temperature is going to be forming at our least substituted side, as we see when we add the propyl group, propane group. Sorry about that. And then for B is the exact same thing. We're going to add the ethyl part into the more substituted side, and then our methyl to the least substituted side. Now D is going to not form this alkylation just because it is a secondary alkyl halide, so we're going to have to forms into an E2 reaction. So now we're looking into the melodic ester synthesis. This is when the alpha proton reacts with the base to form the corresponding enolate. Then the enolate is reacted with the alkyl group, and then we have both ester groups are then hydrolyzed. One of the resulting carboxylic acid groups is then decarboxylated with heat. So now we're going to go to number 8. We're going to predict the intermediate and final products in the following reaction scheme. So we know that our intermediate is going to have an ethyl and a methyl group in the alpha position. And then our final product is going to have a carboxylic acid. Okay, so now we're going to look at our acetoacidic ester synthesis, which is similar to the melodic ester. However, our product is going to finish with an acetone and CO2. So now we're going to look at 9. We're going to predict the product. We know that we're going to have to create an enolate at the alpha position of this molecule, and then we're going to react it with our alkyl halide, which our alpha position is going to form an ethyl, and then we're going to make our acetone derivative. We're going to do the same thing for the next one, for B. We're going to do the same things that we're going to do this twice. We're going to add an ethyl group, and we're going to add a methyl group into our alpha position. Remember that we do create firstly an enolate at the alpha position, and then we're going to have our acetone derivative at the end as a product. So number 10, we're going to fill in the empty boxes with the proper structure reagents. So we know number A is going to be an acetoester synthesis. So we know we're only going to have one ester there. And then the intermediate has to have a methyl group. So we know that it's good, it's right. And then MCPBA is going to oxidize the intermediate, and that's going to be our product. Okay, so we're going to do the last part for this one, for number B, because it's easier. This is the Wittek reaction. So we know the electron withdrawing group is just going to replace the oxygen group here, and everything else is going to pretty much stay the same. For the beginning of it, we know this is the acidic ester synthesis, so we're going to need 2 alkyl halides, primary alkyl halides, to get our intermediate on this. For number C, we know that this is going to be a malonic ester synthesis, so we're going to need also, we're going to need 2 primary alkyl halides as well, but we're also going to need to add a ester at the end since our intermediate does contain an methoxide group. And then the last part is going to be our lithium aluminum hydride, and that's going to create an aldehyde at the end. So now for number D, we know that we need a ketone so it can react with NOH plus heat, and we know that's going to create the aldo condensation reaction. And then with the Grignard reaction, we know that it's going to create an alcohol, and then we insert our alkyl group, which is going to be our phenol. Okay, so now on to our last page. This is going to be showing our decarboxylation process. This is a chemical reaction that removes a carboxylic group and releases carbon dioxide, and then when we tautomerization, we get a carboxylic acid. Okay, so finally, guys, last one, here we go. This is a malonic ester synthesis. So this first, we have to create our enolate, and that enolate is then going to attack our alkyl halide group, and then it's going to create a new ethyl group at the alpha position, and then our ethoxide again is going to attack it's going to deprotonate our H, and it's going to create an enolate, and then our enolate is going to attack again our methyl. It's going to attack our methyl bromide, and it's going to create a new alkyl group, and we're going to have at the end a ethyl methyl group at our alpha position. Okay, so now our oxygen atom, it's going to take an H plus atom to make an alcohol. So then water is going to attack the carbon at the carbonyl atom, and then the double bond at the OH is going to break. Then water comes in again and deprotonizes an H from the water, and so this group can become an alcohol. So now we're going to have 2 alcohol groups here. And then our ethoxide group is going to protonate with an H from the hydronium ion. And then the water, the OH, the one that had the double bond originally, is going to collapse back. And then it's going to kick out our methoxy group. So now we're going to deprotonate the H from the OH group with water. And now we're going to do, again, the whole process again with the other side. So we can kick out the ethoxide group and create an OH. So we're going to do that all over again. So now when we have our product, we're going to do our decarboxylation here, and then we're going to tautomerize it so that we can get our carboxylic acid at the end. And that's our product. Thank you guys for listening. I hope you liked it.